Okay, I feel quite lucky about the previous talks that we had this afternoon because actually they complement quite well what I would like to communicate today, which is a particular case of a dimensionality reduction. I guess we have seen already some examples. So I'm going to present the results of a paper of two authors from 2003. I will mention the reference. I guess the names are Belkin and Niyoki. But I will give this at the end, and this is the outline of the talk. But I'm going to warm up with like some basic ideas. Then we will go to a toy model example. Then I will explain the algorithm, and I wanted to show some examples. But we have seen already some really cool pictures today, so I'm going to shift it to the end, if that's fine with you. And then I'm going to talk a little bit about spectral geometry. So the idea is that we will begin with the notion of manifold, but we have already seen that it's somehow a higher dimensional surface. And it should be linear enough so that we can locally do calculus. But the question, I mean, the manifold area is quite big. Can you hear me? Okay. It's quite big, but I'm going to focus on the area of spectral geometry. And one of the motivating questions of this area is this question posted by Kak, is can you hear the shape of a drum? And what does this mean? There's an operator on manifolds, which is called the Laplacian. And you can think about it as a matrix. And as we have seen, it has this spectral decomposition, which are the eigenvalues. So the question is that, can you recover somehow some information from the eigenvalues? That means, of course, the Laplacian depends on the manifold and on a metric, which is a way of measuring distances. And if you're giving the metric and the manifold, you can construct the Laplacian and get the spectrum, but can you go the other way around? The spectrum often can be thought as like frequencies or like in a drum shape, which is our manifold, so that's the idea behind the question. And you can actually not always go back, but from the spectrum decomposition, you can get the dimension of the manifold, its volume, and the total scalar curvature. So this is the motivating, let's say, setting for spectral geometry, but we want to do something with it, applied to data science. Yeah?
For a total scalar curvature, it means that it's a constant curvature manifold?
No, you just take the integral over it. Sorry?
Repeat the question.
So the question was about the scalar curvature. This is just the sum of the curvature on the manifold, like the integral. Anyway, we want to apply this or see how this can be related to the problem of dimensionality reduction. And this is what we want to discuss in this talk. So the key information, or like this, what we are giving are k points in Rn, where n is quite big. So if you think about the s presented before, n was equal to 3. And the idea is that they lie in an underlying unknown manifold M. And you would like to get somehow as close as possible as this manifold. And the key and motivating idea behind this algorithm is that if you would know the manifold, then the eigenfunctions of the Laplacian actually give you embeddings. So that means the task or the idea is giving the data, you will approximate somehow this manifold, somehow, we will see in a minute how, and then use these eigenfunctions to actually construct the embedding. But we don't know the manifold, so we need to proxy it somehow. And this is the idea that these authors had. And the first step is to build a graph out of it. And as we have seen also in the previous talk, this is based on a similarity measure, so we will put, let's say, for each point one node on the graph, and then we will attach an edge if they are close together. But we will need to define that, and this is what we refer as the graph G. The next thing that we want to do is to construct the graph Laplacian. So we have seen in the previous talk that is also used for spectral clustering, but I want to spend some time like making sense of why would you like to construct such a thing as a graph Laplacian. But once you have this in G, this is just a matrix. So you can apply your linear algebra tooling to compute the spectrum and the eigenvalues, or eigenfunctions in this case, and then you use these eigenfunctions to construct the embedding. So I would be really happy if at the end of the talk, these four steps are clear, and more or less this is the takeout of the talk. But I want to start with a basic theorem from linear algebra, which is the spectral theorem. So let me just spend some minutes here. So if we're given a symmetric matrix in R, symmetrics mean that its transpose equals itself, then, I mean, in general, we have the notion of an eigenvalue, an eigenvector pair, which are pairs of vectors and scalars, which satisfies that relation. So this is something that we have heard a lot this afternoon. So recall the notion of a basis for a vector space Rn. This is going to be a set of vectors which are linearly independent and generate the space. And I'm going to say that a basis is orthonormal if their inner product or the distance are 1 or 0, and they're all orthogonal. So this is something from linear algebra. What is really interesting is that for every symmetric matrix, we can always construct an orthonormal basis from the eigenvectors. And this is the spectral theorem. And it's a really, really powerful theorem, as we will see. More or less, each eigenvalue is real. So I hope this is just the linear algebra we need for the talk. By the way, I encourage you to interrupt me if you have any question, so that we can all follow. So before going to the algorithm, let me recall some properties which is not really known about eigenvalues and eigenvectors. So it's about the minimizing properties that they have. Oh, this is better. So if we are given a symmetric matrix A, we know by the spectral theorem that we have a spectral decomposition. And for later purposes, we would like to see, okay, which vector actually maximize the functional AF. This is a vector inner product with F. This is a scalar. And I'm going to impose the restriction, the norm, to be 1. So I'm not saying it's unique, but let's see what can we say about this. So one thing that you could do is to try to define an optimization problem, like taking a Lagrangian and a Lagrange multiplier. And if you, let me do it roughly, take the derivative, you can convince yourself that if a vector maximizes this, then it must be an eigenvalue of the matrix. So that means, in particular, that the vector which maximizes this functional is actually the eigenvector of the associated higher eigenvalue. And for the minimum one, it's going to be the eigenvector of the minimal eigenvalue. So these are these two formulas, just you can take them for granted that we will use later. But now to the problem. The problem that we're going to solve today is to map these 4 points to a line in a clever way. So the first thing that so let me go before, as mentioned in the first talk, we need to define what do we need to conserve or like to preserve in this mapping. So we want like close points to stay close together. But the notion of closeness, of course, depends on a distance. So the distance function that we're going to use in this case is the first near neighbor. So how does it work? We have our points, and the first near neighbor of 1 is 3. So I put an edge. For 2, it's 1, so I attach another edge. And from 3 to, it was already 1. And then from 4, I attach an edge to 1. Was this construction clear? I just take the nearest neighbor and attach an edge. And we get a graph. So the step 2 is to construct two natural matrices which actually define the graph. So this is what is called the adjacency matrix, which is a matrix where it carries 1s or 0, indicating whether there's an edge or not. So this indicates there's an edge between 1 and 2, and this indicates there's no edge between 2 and 3. And on the other hand, we have the degree map, which actually summarizes how many edges each node has. So node 1 has 3 incoming edges, and the other have 1. And the step 3 that we wish to clarify is that if you take this difference and say that this is the graph Laplacian, actually this is the key actor in this embedding problem. So we're going to define now the graph Laplacian as taking the difference between these two matrices. And in the next step, I mean, now it's just purely the algorithm, and then we will see why this actually works. We consider the generalized eigenvalue problem given by graph Laplacian times f equal lambda df, which is equivalently, you can invert this d to this other relation, and then you will need to find the eigenvalues, which you can convince yourself are 0, 1, 1, and 2. And then I will consider not the eigenvalue 0, but the next one, which is lambda 1 equal 1, and consider an eigenvector of such one. There are many. I just choose one, which is in this case 0, minus 3, 1, 2. So maybe I verify that this is true. And also, can you guess which is the eigenvector of the eigenvalue 0? The vector of 1. Yeah. So this is actually something that we will use later. So if you plug the vector 1 over 1, this will give you the eigenvalue 0. And if we consider this as the coordinates, I mean, if we consider y, or this eigenvector, as a function which assign to each index its associated coordinate, then we will get, like, I will map 1 to coordinate 0, minus 3, 1, and 4. So this is actually, and 2. So actually this did the job of mapping what we had in 2 dimensions to 1 dimension. So this is the basic idea of spectral clustering, of spectral embedding. So let me summarize. Step 1, you construct the graph where you define a similarity function. There are 2 usual candidates. You can use either the Euclidean distance or nearest neighbors. Then you can choose weights. In this case, we choose the weights 1 on the adjacency matrix, but actually you can take these exponential or Gaussian weights, which actually we saw before for the spectral clustering. And as a spoiler, actually these coefficients or these weights actually come from the heat equation on the manifold that we don't know. So that hopefully at the very end we can explain why this is a natural choice. Of course, t is a parameter that you want to fix. And then you construct the graph Laplacian, but for that you need 2 ingredients. The first one is the matrix D of degrees, which in more general is just the sum of the rows of the matrix W. And then you take the difference and consider the eigenvalue problem. This is a matrix. You compute the eigenvalues and the eigenvectors and construct the embedding as follows. You take out lambda 0 equals 0, which will always appear as an eigenvalue. If the graph is connected, it will just appear once. And then you can use, as before, you are going to define an embedding of degree m, meaning to a space of dimension m, if you take the first m eigenvectors. And this will work. So why does it work? Well, the easiest case that we actually want to tackle is just mapping everything to a real line. So assume that you have constructed your graph, which it's fine. So what's the idea? How do I map it? So let's say a natural candidate would be to consider this functional j, which actually takes the difference between the 2 points, which are mapped. So the y coordinates are already in R, times the weight. If the weights are 0, that means the points are far away. This function doesn't see anything. But if the w is 1 in the easy case, then you need to minimize this. So it's natural. And the key point is that you can express this functional as the relation y transpose Ly, where L is the graph Laplacian. So this is why you say, okay, if I want to consider this minimized, like let's say, locally minimizing property, then the graph Laplacian is actually the matrix that I want to consider. For a lot of people, that's enough argument, but I want to show that this has a deeper geometrical significance. I mean, it just works. So again, the problem reduced then to find a minimizer of this, which we can rewrite in terms of the inner product as Ly inner product with y. And this should, let's say, be similar to what we saw on the first warming slide, where we see, okay, up to these conditions that I'm going to mention later, this is actually, if I consider this problem, what I need to consider is an eigenvector of the Laplacian. And since I have the arc mean, it's going to be an eigenvector of the lowest eigenvalue. But we have 2 restrictions. The first one is this one, which just fixes the scale. so it doesn't have anything deep. But the second condition actually eliminates the trivial solution y equals 1, so that takes out the 0 eigenvalue, and can also be seen as a translation invariance restriction. So everything that is here is what we want to solve, and by what we did with the Lagrangian, we saw that this is an eigenvalue of this problem. Okay? So this is how it works for m equal 1. From m bigger than y, we can just vectorize everything, meaning whenever we have a vector, we put a matrix, and whenever we have a sum, we put a trace. I'm going to share this slide, so I don't want to spend much more time here, but it just works. So again, I wanted to show some examples. Guess which example? Of course, the S-curve, but I'm going to put this at the very end because we already have seen like the shape that we will get, but I would like to comment on how this is implemented in scikit-learn. But really about the Laplacian. So what's the Laplacian? So if you have studied some calculus, this is a second-order differential operator, which looks like the first line, which is just taking the sum of all of its derivatives. So that's pretty nice. And that's in Rn, which is a flat space. If I consider like a surface, then what it's, let's say, encoding the curvature, how it twisted, is the metric, so to say. So when I have a manifold, then the Laplacian will be something of this sort, plus some coefficients, and lower order terms, which are complicated, but we don't care. And an important and fundamental theorem in spectral geometry is that we have an exact same result for the Laplacian as we have for the matrix, in the matrix case. So let me state this theorem, which I will also mention a nice reference about this topic. So the first thing is that L, as the derivative, is symmetric with respect to the inner product, which is the integral. So usually we think about inner products about just multiplying the components and taking the sum, but we can always generalize this as taking the integral, because the integral should mimic somehow what a sum is. And if M is compact, meaning if I can put my surface in a box, roughly speaking, on the one hand side, there exists an orthonormal basis on functions, which consists of eigenvalues of eigenvectors of the Laplacian. Moreover, each eigenvalue is real. So as innocent as it might look, this is a really powerful theorem. I mean, just the fact that the spectrum is discrete is already important, because it might happen in some cases that you don't have like discrete numbers, but just rather a continuum. So you cannot say what's the first one and what's the second one. But in this case, you can do. So if you have the problem of embedding a known manifold M, a surface, into R, then what can we do? Well, first we need to estimate, okay, what would be the idea? So we want to bound the difference at the embedding space by something. So if I take X and Z in M, which are closed, what I want to have is that on the embedding, after the embedding, they remain closed. So one can actually show that if I take a function mapping to R, then you can bound the difference of any function by the distance on M plus the derivative of F plus lower order terms. So basically what is, let's say, measuring how much I can shrink or expand my points in R is the derivative of F on M. So a natural candidate would be say, okay, let us assume that, or what we want is that F's preserve locality on average. And I think with respect to the first talk, let's say trying to see what is preserving is kind of tricky, because it's really about preserving locality on average. So we need to solve this problem. Find an F which minimize this functional. We can try to mimic what we did for the matrix case and just try to put it into like arc-min problem. So I don't know, back for if you guys remember from calculus, we can use something which is the Stokes theorem, which is basically the fundamental theorem of calculus that you can integrate a derivative to show the following. This integral actually coincides with the inner product of the Laplacian times f of f, inner product with f. So recall that this inner product is this integral. So the computation is not important, but what is important is that then if I take the arc mean of this thing is the same as taking the arc mean of this thing, and we know, as if we would mimic the result from linear algebra, that it should be an eigenvalue of the Laplacian. So actually, this is a motivating, or let's say what's relating the Laplacian on the manifold, which we don't know, to the graph Laplacian. But the question that is remaining is, okay, you talk about something, a Laplacian given on points, and something in a manifold. And let's say, what's the relation? Well, this gets a little tricky. What I want to say, let's say, two ideas. The first one is actually that the Laplacian is taking a derivative on the graph. So what could be a derivative on the graph? Well, it's defined by the boundary operator. We just take the difference between two edges. So for example, if I take any directions, so I construct a directed graph from the graph, so I put some arrows around. So the first row says, okay, there's an arrow which starts at 1 and ends at 2. And the second one is there's an arrow that starts at 3, begins at 1 and ends at 3, and so on. So this is the way you could mimic like taking a derivative. And then if you take the combination, which is take the transpose of this derivative, which is what you do for the Laplacian, which is, the Laplacian is the divergence of the gradient, you get precisely the graph Laplacian. So this is how you can see it as a differential operator. And let me finish the first part of this talk talking about the relation with the heat kernel. So we have seen in the previous talk that there are some weights, which are these Gaussian decaying functions, that also appear in the algorithm. Actually, it's really nice on the original paper that they play around with the parameter t, saying, okay, which kind of, or I can tune this parameter to get a better embedding. But this is not something that comes for free. It actually comes from really geometrical interpretation. So once you have the manifold M, you can talk about the heat equation on it, which somehow will model the flow of, let's say, heat on this surface. So if you have a, let's say, engineering background, it's the same idea for a function which depends on the position on x and time. Then you will take the derivative with respect to time plus the Laplacian, and you equate this to 0. And you impose some initial condition. For example, at time 0 should be some value f of x. So this is the heat equation on manifold, and there's a, not really explicit, but there's a trick of finding a solution of the heat equation. And it's via the heat kernel. So what does it mean? Every solution of this equation can be expressed as the integral of the initial condition f times a kernel function. And this kernel function is called the heat kernel. And it has a partially explicit form. So the first part is, let's say, the heat kernel of the Euclidean space, which if you have studied this, I mean, you have a power of 4 pi times t to the minus dimension of m over 2, plus this exponential term on the distance of the points. But on the manifold, you have some corrections. The first correction is just a function which is 1 on the diagonal, and you can expand this in higher powers of t. So actually, the heat kernel carries basically all of the information of the Laplacian. Moreover, at the very beginning, when I talk about can you hear the shape of a drum, this, the way you recover, for example, the dimension or the volume is through this heat kernel expansion. Because what you would do with your spectrum is build up this heat kernel and see how this take the expansion when t equals infinity, so to say, and you can read from the coefficient, okay, this should be the dimension, this should be the volume. So through this guy, you can actually recover all of information. So it's actually, with the heat kernel, you can partially hear the shape of a drum. And if you do some approximation, let's say tricks, I will encourage you to go to the original paper for the calculations. You will see that you can actually transform this Laplacian to something of the form d minus w. And the natural weights actually are these exponential weights. So roughly speaking, you can think, okay, if I take the weights equal to 1, I still get a differential operator by just taking the boundary, as we did before. But somehow, let's say, we can say that this actually shows that the graph Laplacian is approximating the Laplacian in this unknown manifold. So I hope this gave, I know there's a lot of buzzwords, but the essential idea is that there's a natural way of embedding manifolds or surfaces into low-dimensional spaces via eigenfunctions of the Laplacian. And the trick is, okay, approximate your manifold with a graph and try to do this in a discrete manner. So I guess from the theoretical point of view, this justifies the choice of weights. And let's say summarizing what the spectral embedding wants to do is to preserve locality on average. So maybe just to finish and maybe to show some connections to scikit-learn, because of course at the very end we want to use this. We have already seen like some implementations, but I just want to take this example and try to do it with Python, which is somehow easy. So this is what we got. And for the spectral embedding, we need to construct the Laplacian. So this is what we do. The only input is really the adjacency matrix, because then the degree matrix you can take by summing the rows, and then you just need to take the difference. So the only input that you need is this matrix W, which defines your graph.
Should we make it larger?
Yeah. Is it better? I will probably sit. So this is what we have. And then there's a function, which is spectral embedding with, let's say, no capital letters. And this is a really general form. So what it receives is the adjacency matrix, W. The number of components means where do you want to map it. I want to map this to a line, so the dimension is 1. I don't want to normalize the Laplacian, and I want to drop the first eigenvalue. And okay, there's a solver option, and this is what we get. So we get other coordinates, which are not the ones that I have, usually because these are already normalized. So I just want to verify that this actually satisfies the eigenvalue problem. So I just see if the result that scikit-learn gave me actually coincides with analytically what I would like to do, and it's true. So this is just a simple toy model to show how you can implement it. But in scikit-learn, you have let's say, a capital letter spectral embedding, which is, let's say, less general, and that's what we have seen today, because what it inputs is just the number of nearest neighbors. So here we also have this really nice S curve that we can move. And so this is the example that's already been studied here. And again, I took this from scikit-learn documentation, which I encourage you to do. And what PCA is doing, as we've seen before, is just take the principal component, so just wants to maximize the variance, so it will take this, and this is actually what we get, so it's not very surprising. And as we have seen, before, if we have now our spectral embedding, we will get something of this sort, which is hard to interpret what it's preserving, but I guess I hope I can convince yourself that it's a local average, preserving locality on average. But here we have used 6 nearest neighbors. So I'm going to try 1,500. Can you guess which kind of shape are we going to get if we take a lot of neighbors? I mean, somehow this is measuring how local do I want my problem to be. So this is going to be quite global. So I want to preserve locality, but here locality means, okay, how close my points are going to be. But if I take a lot of points, well, this becomes just a global problem. So this is like somehow to play around with these parameters. I'm going to share this notebook as well. And again, we have the example of the sphere that we were teased before. So here we have in the scikit-learn documentation the sphere where it has 2 holes, this one and this one. And actually it's quite fun. I don't have time to do it here, but try to close these holes and do the embedding. You'll see and understand a little bit how does it work. So the first thing that we can try is PCA. And what we will get is something of this sort. And it's really not surprising because we cannot really rotate this axis to unroll the sphere. So let's say this is not going to work for our purposes. But if we do it now with the spectral embedding, then let us see the results. Then it's something like this. So it's unrolling the sphere, and you can see 1 hole here, 1 hole here. This is the boundary of the circle, and this is the slice that we cut. So let's say this is how you can see how this is actually unrolling. And maybe to comment about the functions, I'm not sure, but I guess we can just define the number of components and the number of neighbors. So I guess this is not as flexible as just inputting the adjacency metrics, but you can still use the, let's say, lowercase function for it. And so I hope you can play around with these notebooks, which I hope to share. And last but not least, I will indicate some references. So the first one is the paper by Belkin and Yogi, which I've tried to follow so that if you would like to read it, you might get some hints. It's fun to go to the article of Kak, where he posts this question about, can you hear the shape of a drum? I guess this is just to teach you about spectral geometry. And if you want to have some more details, then the book of Steven Rosenberg, it's quite friendly. So I hope this somehow helped you and complement the other talks, which were great. And I think I'm going to finish with this.
Okay, thank you very much for giving a talk. I think we should have taken yours as first, so maybe to have the theoretical grounding.
No, because then you wouldn't see where you're going, and let's say, okay, eigenvalues, but that's
but it's becoming more mathematical over a while. I like that it's like continuous development. Nevertheless, so we still have time for questions or Q&A. Are there questions or remarks? Okay, 3. But actually, you were first, and then you, and then you.
So can you say why these eigenmaps are good choices for embedding?
So what the idea is that if I demand to have a bound for locality on average, then you will have to solve this problem. But this problem is equivalent to finding the arc mean of this, which is an inner product. And as we saw in this first slide, if you want to find an arc mean of an inner product, This is just a very warm-up. This must be an eigenvector of your operator.
This generalizes to more than one dimension.
Yeah. And, but even in the linear case, you can just vectorize what we did, let's say this motivating example, to motivate the general case.
What happens? What happens if I take a fully collected graph?
A what?
A fully collected graph, so with all weights one. Your very first example, if I connect all the edges.
Then you will try to solve a global problem, and I guess you get something like PCA. This is what we did with the S. So let's say my intuition says that. I don't know if, of course, it's not the same as PCA, but it will try to map it globally. Sometimes it will work, sometimes it won't, because I cannot map a sphere, for example, to a plane. There's curvature obstructions for it. So, but somehow the number of neighbors or the distant functions will tell the problem or will define how local do I want to remain.
Hi. For industrial applications, I often use dimensionality reduction using thousands of input dimensions. How does this behave in these large applications?
Actually, I don't know about the order of complexity, but what I saw in the first talk is that it was pretty fast. So with respect to the other methods, I don't know if this, I mean, of course, it depends on what you want, but what I can say from what I've seen and from the documentation is the overall is quite efficient because it's, yeah, more or less, I mean, if you just compare it to others, it can compete. So, but I don't know, let's say, the true benefits.
To which scale have you applied spectral embedding?
I come from spectral geometry, so I haven't used this much in real-life problems. But I would like to. So.
And yours, Evelyn, was medium-sized too, right? So not more than, you didn't have like really huge data you were running the embeddings on, right? So you also implied, yes. This is my experience also, that these methods, while they're really sophisticated and can capture quite sophisticated characteristics in the data sets, they just work on small data sets. So once you have 10K of data points, it doesn't work. I don't know how it's in higher feature dimension. I mean, you stated 1K of features, but that's like in the machine learning, we are talking about millions of features sometimes. So this is a bit unfortunate. So are there any more questions or remarks regarding application of these methods? No? Cool. Then thank you very much. And thank you, Juan, again.
Thank you.